Hello everyone, my name is Haotian Zhang. This work is covered with Mengfei, Yu Lei, and Jiang Ming from the University of Texas at Arlington. The title is One Size Does Not Fit All: Security Hardening of MIPS Embedded Systems via Static Binary Debloating for Shared Libraries. So first, let me introduce the background and motivations. You may already know the IoT devices are already an essential part of our life. We have router, security camera, voice assistant, and drones. For example, here is a router. And during the development of the firmware, the developer cannot live without the third-party libraries. For example, inside the router, it can have C libraries, C++ libraries, OpenSSL libraries, and lots of third-party libraries. We can dynamic linking a library or static linking a library. However, static linking is not a solution to put such as Apache, BusyBox, and many of your own programs into a whole memory. We have to use shared libraries in the firmware or in other projects. However, the design of the shared library is one size fits all. It fits your project, but it's often overfitting your project. For example, for the C libraries, it provides all the possible basic functionality for a program to use. However, you cannot use all the functionality of a C library. Do you think a router can use all the functionality of a C library? In our experiment, we can remove 36% of code in the multi-libc library of a router. For the shared library bloating issue, there are many thin version shared library being invented to solve the issue. However, for a particular firmware or project, that's not enough. Those shared libraries still bloating. So what's the benefit when we remove those unused code from the firmware? For the developer, smaller firmware means smaller hardware requirements. That means we can use a smaller RAM and ROM chips. For the user, it means faster booting speed, read from ROM is slow, and more secure. We remove potential attacking surface. Less gadget can be used by attacker to construct the ROP chain without the additional overhead. Also, debloating shared library is promising in IoT devices. If we debloat shared library in a PC environment, an end user can install any software they want. And if the new installed software uses the removed feature from the shared library, it will result in a crash. However, for an IoT devices, most likely it will not provide a package manager for end user to install new software. And the update mechanism of the IoT devices is often the whole image update. That means if we debloat a shared library for firmware, it often will not compromise the forward capabilities. There are also existing debloating work available, such as Piecewise from Usenix Security 18, Nibbler from ACSAC 19, Blanket from PLDI 20. However, they have different assumptions and requirements. For example, for the Piecewise, it has customer compiler to compile additional meta information into shared libraries, and during load time, their customer loader will based on that meta information to remove or mask those unused functions, which increase the load time slowdown. For the Nibbler, they have assumption that the shared library has the debugging symbol, and based on that debugging symbol, they remove unused functions from the shared library. For Blanket, it uses the Intel pin to dynamic debloat the shared libraries, which at any given time only the needed function is visible or executable. So on average, it can reduce a large percentage of the code. However, the requirement using the Intel pin and the large overhead is not feasible in IoT devices. Our work, we call it mu-trimmer. We don't have assumption to have the source code or debugging symbol, and we don't need any runtime support. We debloat at the basic block granularity because the shared libraries tend to have heavy optimization, and functions may have multi-entry or the functions may share a basic block with each other. So we debloat at the basic block level to avoid the function identification challenges. So here is the overview of the MIL trimmer. MIL trimmer can be separated into two parts. The first part is collects the needed API by the firmware. The second part is analyze what basic block should be preserved for each shared library. So for the first step, we need to do the pre-processing for the firmware. So after we have a firmware image, we first extract the file system from the firmware by using a tool called binwalk. And then we will use tools readelf and nm to get the import table and export table from the applications and shared libraries. Next, before getting the API required by the firmware, we need to build the library dependency graph. So here is how and why we build the library dependency graph. We take HTTPD program as an example. HTTPD is Apache's web server, and this program depends on 5 different shared libraries. You can see from graph A. And among these 5 different shared libraries, the shared libraries also has the interdependency. For example, the libpcre, the pink one, also depends on the uclibc C library. We take libpcre shared library as an example. It depends on 18 functions from the uclibc, such as strchr, to upper to lower functions from the C library. However, after we debloat the libpcre based on the API required by HTTPD, we can remove 32% of code in libpcre shared library. And we can find out the remaining code inside the libpcre is no longer using the to upper to lower functions from the uclibc shared libraries. So if we want to only preserve the needed code for each shared library, we need to debloat the libpcre first, and then we can debloat the uclibc. So in this example, we need to debloat the libpcre library and libapr utilities libraries first, and then we can debloat the libapr and the libexpat shared library. Finally, we can figure out what's the needed function inside the uclibc C library. We need to debloat the shared library in its topologic order. That means we need to recurrent debloat the shared library with no incoming edges until we debloat all the shared library. In that way, we can preserve only the needed code for each shared libraries. So after we collect the needed API for each shared libraries by the entire firmware, we took those needed API for each shared library as the starting point to begin to build the inter-procedure control flow graph for each shared library to analyze what basic block should be preserved for them. So in order to build an inter-procedure control flow graph, the main challenge is how to deal with indirect control flows. Indirect control flows is the control flow indexed through a register or memory. Here is an example from MIPS architecture. JALR stands for Jump and Link Register, which is similar to a call instruction. This one will call to address saved in the T9 register. In order to solve the possible indirect control flow targets, we need to know the possible value saved in the T9 register. The above instruction will load the address from memory and save it in the T9 register. However, solving the indirect control flow is not easy because this value can be then saved in a stack and loaded through a pointer. Solving indirect control flow, one way to solving it is with value set analysis. However, value set analysis have high false positive. Sometimes value set analysis cannot find enough restriction to solve the indirect control flow, which will result a very wide range of possible indirect control flow targets, which make debloating infeasible. For example, bin trimmer published in DIMVA 19 using value set analysis to do the binary code debloating. However, they only evaluate their work on two very tiny programs with just hundreds lines of code. Take one step back. Even if we get a very high accuracy indirect control flow analysis results, it's still not enough for the debloating, because we also have callback issue. Here is an example qsort, which is quicksort in C library. It can accept a function pointer comparator. If we call qsort in our code, you can see there is no direct control flow called to the link to the comparator, because the actual control flow is inside the qsort function, which is out scope in our code. But for our debloating, even if we didn't find a control flow to comparator, we still need to preserve the comparator in our code. So how should we do that? Previously, another way to limit the indirect control flow targets is using the address stored in relocation table. They call it address taken functions. However, shared libraries are position independent code. That means most of the shared library functions are stored in the relocation table. If we preserve all the functions in the relocation table, we cannot debloat anything. We have to trim it. So our strategy is, instead of focusing on solving the indirect control flow, we focus on how an indirect control flow targets read from the memory. We focus on the source of the indirect control flow. Shared libraries are position independent code, so we categorize how the position independent code loads the indirect control flow targets from the memory. In that way, we will figure out what basic block should be preserved in our debloating. So here is a graph. We classify all the possible ways indirect control flow targets can be loaded from memory. So for the shared libraries, it's position independent code, and position independent code mostly loads the targets through global offset table entry. For most cases, it's intra-module loading, which means the load instruction is inside the current module. Cases such as you are using function pointers, jump tables, or virtual functions can all be the intra-module loading. However, cases can happen for the inter-module loading, which means the load instruction is outside of the current module. For the global offset table itself, it's a compiler-generated low-level structure. When you high-level programming in C or C++, you cannot get a direct reference to the global offset table. However, compiler can do that. For example, the virtual table is another compiler-generated low-level structure. It can be referenced to partial of the global offset table, which can result to inter-module loading. Another scenario is the exception handling, which the exception handler is incorporated by the GCC and the C++ library. These are the scenario for the inter-module loading. We also have the automatic calculation, which is due to compiler optimization to reduce the number of the global offset table entry. And we also have special cases such as when the function pointer are saved as read-only global variables, which means the function pointers will be saved in a data section, which is also some cases load from outside of the global offset table. After we categorize all the possible ways loaded from memory, we have a set of indirect control flow targets, but we didn't solve the indirect control flow because we didn't know for each indirect control flow targets is used in which indirect control flow. Or maybe this target will be used outside of the current module. It's like building a control flow graph without some edges. It didn't solve the indirect control flow, but it is enough for us to debloat. We already know what node should be preserved. Here is a study of the distribution of our address loading types in spec CPU 2070. And as you can see, most of the type is the type 1 loading. and only the share library written in C++ has the type 3 or type 4 loading, which is virtual function and exception handling. After that, we will begin to remove unused basic blocks. For basic block erasure, those basic blocks not included in the control flow graph can be safely removed. And our strategy is simply override this actual basic block with a single batch illegal instructions. The benefit is that if any attempt to run the erased code will trigger an exception, and we are immediately aware of our implementation error. So our first experiment is empirical correctness testing. We have spec CPU 2017 integer dataset and some firmware applications we selected, such as Apache and BaseBox. And after the debloating on spec CPU, we can remove 66% of the share libraries on average, and we can remove 55% of share library code for firmware applications. And after the debloating, we run the reference dataset for spec CPU program and official test cases for firmware applications, and they all have the consistent behavior without error. In the second experiment, we compare ourselves with static linking because we think static linking is almost the best achievable. As you can see, for Apache Web Server, static linking can remove 42% of shared library code, and MuleTrimmer can remove 40% of shared library code, which static linking is a little bit better than us. In experiment 3, we test the gadget reduction after the debloating, and as you can see, the total gadget reduction is almost identical to the how much code we removed. In experiment 4, we debloat a real firmware TP-Link Archer A10, which contains 25 share libraries and 75 applications. Overall, we can remove 29% of share library code, and we found libc is never being imported by any applications, which is interesting. In future work, we want to apply MuleTrimmer to ARM architecture. Right now, due to challenge of disassembly, such as ARM's constant pool or thumb instruction set, which cannot guarantee the correctness. And we also want to rewrite the debloated library rather than overwriting it, which is another challenge topic for the binary writing. Thank you.